So in this video, we're going to look at an example where we're testing a hypothesis regarding the difference of two means where we have independent samples. So walking in the airport. Do business travelers walk at a different pace than leisure travelers? Researcher Seth B. Young measured the walking speed of business and leisure travelers in San Francisco International Airport and Cleveland Hopkins International Airport. His findings are summarized in the table. So we have the type of traveler, which is either business or leisure. And so the mean speed in feet per minute for business travelers was 272 feet per minute, and for leisure travelers was 261 feet per minute. The standard deviation for business travelers was 43 feet per minute, and for leisure travelers was 47 feet per minute. And the sample size was 20 business travelers and 20 leisure travelers. So we want to answer these questions. Question A, is this an observational study or a designed experiment? Question B, what must be true regarding the populations to use Welch's t-test to compare the means? And then part C, assuming that the requirements listed in part B are satisfied, determine whether business travelers walk at a different speed from leisure travelers at an alpha equals 0.05 level of significance. So let's take a look at question A and question B on this page, and then we'll look at question C on the next page. So is this an observational study or a designed experiment? Well, in this particular case, we have an observational study because this researcher is just observing the business and leisure travelers. The researcher is not influencing the results of the walking speeds. So this is an observational study. What must be true regarding the populations to use Welch's t-test to compare the means? So if we want to do a hypothesis test for the differences in the two means, what's going to have to be true in order for us to be able to do that? Well, the issue is that we have two small sample sizes. We only have 20 business travelers included in this sample. We only have 20 leisure travelers included in this sample. That's not 30 or bigger. So in order for us to be able to use Welch's t-test, we have to have normal populations. So the walking speeds of business travelers have to be normally distributed, and the walking speeds of leisure travelers have to be normally distributed, and also there can't be any outliers. So we have to have normal populations. Now, assuming that these requirements are met, we want to conduct a hypothesis test to determine whether business travelers walk at a different speed from leisure travelers, and we're going to use an alpha equals 0.05 level of significance. So, we need to start by establishing our null and our alternative hypothesis. So if I let population 1 represent the business travelers and population 2 represent the leisure travelers, then my null hypothesis is going to be that mu1 equals mu2. So the mean walking speed of business travelers equals the mean walking speeds of leisure travelers. We're asked to determine whether business travelers walk at a different speed. So our alternative hypothesis is going to be that mu1 does not equal mu2. Again, 1's representing business, 2's representing leisure, and we're checking to see are they equal or are they different. Now remember, a second possibility here is we could structure this as mu1 minus mu2 equals 0 versus mu1 minus mu2 does not equal 0. This is the form our textbook uses, whereas this is the form StatCrunch is going to use. So that's why I'm mentioning that. So that's step 1. Now we're assuming all of the conditions are met. We will assume that these individuals in these samples were randomly selected. They are independent from each other, both within the samples and between the two samples. and we're assuming that these data come from populations that are normally distributed. Now we need to choose a level of significance, and we were told in our problem to use alpha equals 0.05. So we're using a 0.05 level of significance. So the next thing we have to do is we need to calculate our test statistic. Whether we're doing a classical approach or the p-value approach, we need to calculate the test statistic. So again, our test statistic is x bar 1 minus x bar 2, that quantity, minus mu sub 1 minus mu sub 2, that quantity, over the square root of s sub 1 squared over n sub 1 plus s sub 2 squared over n sub 2. Now if mu 1 minus mu 2, if mu 1 and mu 2 are equal, then mu 1 minus mu 2, that part will be 0. So mu 1 minus mu 2 is going to be 0 if the null hypothesis is true. Now, so we were told that x bar 1 is equal to 272. We're told that x bar 2 is equal to 261. So we have 272 minus 261 minus, again, mu 1 minus mu 2 will be 0 if mu 1 and mu 2 are equal. And we're going to divide that by the square root. Now, we were told that the standard deviation of the business traveler's walking speeds was 43. So I'm going to have 43 squared divided by 20. Again, we were told the sample size for the business travelers was 20. Plus, the standard deviation for the leisure travelers was 47. So we're going to have 47 squared divided by 20. Again, the sample size for the leisure travelers was 20. So I need to do this calculation, and I'm going to have my calculator. So I'm going to bring in my calculator, parenthesis, 272 minus 261, close parenthesis, minus 0, I'm not going to type, divided by the square root of 43 squared divided by 20 plus 47 squared divided by 20. And that gives me 0.772. So our test statistic is approximately 0.772. Okay, so what do I do with that? Well, if I'm using the classical approach, I need to find the critical value to compare that to. So our critical value is going to come from a t-distribution. Now, our sample size for the business travelers was 20. Our sample size for the leisure travelers was 20. So if I take 20 minus 1, that's 19. 20 minus 1, that's 19. So we're supposed to use the smaller of n1 minus 1 or n2 minus 1. In this case, they're both 19. So we have 19 degrees of freedom. Now, this is a two-tailed test, and we are using a 0.05 level of significance. So that 0.05 is going to be split between the two tails. So half of 0.05 is 0.025. So we're going to have 0.025 in each tail. So we need to figure out what are these critical values. They'll be the same value, except this one will be negative, this one will be positive. So how do we find those values? Well, we can either use the student's t table from the back of the book. We can use the inverse t command on our calculators if we have that command available, or we can use the t calculator in StatCrunch. Any one of those three we can use to figure out that critical value. I'm going to use the inverse t command on my calculator. So if I go to inverse t, in this case my area in the left tail is 0.025. I have 19 degrees of freedom, and so if I calculate that, I get negative 2.093. So this value is negative 2.093, which means this one is positive 2.093 by symmetry. So if I compare 0.772 to this, 0.772 would be around here, which is not bigger than 2.093 or smaller than negative 2.093. In other words, it does not fall out here in the tails, so we do not reject the null hypothesis. Now, if we want to use the p-value approach, once we know the test statistic, I'm going to use my t-distribution, again with 19 degrees of freedom. Now, the p-value will be the area outside of the test statistic and its opposite. So our test statistic is 0.772, which would be around here. Its opposite is going to be negative 0.772, which would be about here. So the p-value is the total area in those two tails. Now those two areas will be the same thing, so if I find one of them, I can double it, and that will give me the total area. So how do I go about figuring out what the area is, say, in this tail? Well, I can approximate it using student's t-table from the back of the book, or I can use the tcdf command on my calculator, or I can use the t-calculator in StatCrunch. I'm going to use the tcdf command on my calculator. So I want to find the area from 0.772 to a big positive number on a t-distribution that has 19 degrees of freedom. So if I pull my calculator back in, I'm going to distribution and tcdf. So I'm going from 0.772 to a really big number, and I have 19 degrees of freedom. So if I find that, that is 0.2248 approximately. So this area here is 0.2248. By symmetry, that means this area here is also 0.2248. So my p-value is going to equal 0.2248 times 2. So if I take that times 2, that is 0.4496. We have a p-value of 0.4496. Now that is certainly bigger than our level of significance 0.05, so that tells me also do not reject the null hypothesis. So our question was, does mu1 equal mu2, or is mu1 not equal to mu2? Well, we did not reject the null hypothesis. So our conclusion is that business travelers and leisure travelers walk at the same rate. The difference in their walking speeds is not statistically significant. So again, as far as we can tell, business travelers walk the same speed as leisure travelers. Now, we could also do this test using technology. So I want to show you that next. So on my calculator, I can go to Stat and Tests, and I can do a 2-sample t-test. So when I go to 2-sample t-test, I have two options. I can either have data or I can have statistics. Well, in this particular case, we have the summary statistics. So again, for the business travelers, we were told that the mean walking speed was 272 feet per minute, and the standard deviation was 43. The sample size was 20. For leisure travelers, we were told that the mean walking speed was 261 in that sample with a standard deviation of 47. And the sample size was also 20. For our alternative hypothesis, we wanted the not equals to. And for pooled, we're going to leave that option on no. And so if I calculate, I get our test statistic, 0.772, which agrees with the result we obtained by hand. Now our p-value here varies a little bit, so we get 0.4448, whereas by hand we got 4496. So 4448 is a little different from 4496, so I want to explain the reason for that difference. The reason for that difference is here with the degrees of freedom. If you take a look at the degrees of freedom, the calculator says the degrees of freedom is 37.703271103. So why is that different from our degrees of freedom? Well, we're using a conservative approach to do this, and this is pretty common for a by-hand approach if we're doing by-hand calculations. But the way the calculator is calculating the degrees of freedom is a little bit different. So here we have a note about degrees of freedom. When we perform inference about two means with independent samples using technology, the degrees of freedom are calculated as follows. So the degrees of freedom with our calculator, and for that matter with StatCrunch or any other technology, is going to use this much more complicated formula. So the degrees of freedom is calculated by taking s sub 1 squared over n sub 1 plus s sub 2 squared over n sub 2, and then we square that, and then we divide that by s sub 1 squared over n sub 1 squared over n sub 1 minus 1 plus s sub 2 squared over n sub 2 all squared divided by n sub 2 minus 1. If we were to do that, we would get the degrees of freedom of 37.703271103 that the calculator obtains. Well, doing that by hand is a lot more complicated, so if we're doing this by hand, we're generally just going to use the smaller of n sub 1 minus 1 and n sub 2 minus 1, which is a more conservative approach, which means it's going to be less likely that we reject the null hypothesis in error. Now, the trade-off for that is we have to recognize that technology is not going to give us the exact same p-value that we get if we do this by hand. So we can also do this in StatCrunch, so let's take a look at that. So in StatCrunch, we're going to go to Stat and T-Stats, and when we point at T-Stats, we have three options: one sample, two sample, or paired. Well, in this case, we have two samples, so we're going to use that option. Now, to distinguish between whether we use two sample or paired, in the previous section, we were looking at paired data. The data were dependent. In this case, the data are independent, so we have two samples. Now, in this case, we have summary information, so we're going to go with summary. So since I have summary information, I'm going to just fill in what we know. So again, for sample 1, that was the business travelers. The mean was 272. The standard deviation was 43, and the sample size was 20. For sample 2, that's the leisure travelers. We had 261 for the mean, 47 for the standard deviation, and again 20 for the sample size. We're doing a hypothesis test, and again, this is where the structure of the hypothesis test looks a little different, but it's equivalent. So we have a null hypothesis of mu1 minus mu2 equals 0 versus an alternative hypothesis of mu1 minus mu2 does not equal 0, as opposed to less than or greater than. So leave that at not equals to. So in this case, all we have to do is select compute. And so when we do that, we get the test statistic, which is 0.772. That agrees with both our by hand calculation and the calculation from the TI calculator. And we get a p-value of 0.4448. Now that agrees with the p-value from the calculator, but that is slightly different from our conservative p-value that we obtained by hand. Notice that the degrees of freedom in StatCrunch agree with the degrees of freedom from the calculator, because both of those technologies are calculating the degrees of freedom using that more complicated formula, not using the lesser of n sub 1 minus 1 or n sub 2 minus 1 like we've done by hand. So again, there's the trade-off. It's a little simpler using the n sub 1 minus 1 or n sub 2 minus 1, whichever's less. That's simpler, but that's going to not be quite as accurate as the technology will give us. So anyway, this is how we go about doing the hypothesis test if we're using StatCrunch. Again, like before, we have to know what to do with these results. So we have to know to compare the 0.772 to the critical values, negative 2.093 and positive 2.093, or we have to know to compare the p-value to the 0.05. And the fact that this p-value is bigger means we are not going to reject the null hypothesis. So again, the technology will do the calculations. We still have to draw the conclusions ourselves.